Hello, everyone. So it's fair to say that up to now in Earth climate simulations as well as exoplanet climate simulations, convection as well as the clouds that it creates are still a big source of uncertainty in the models. And so I think that's why for today's talk, the organizer asked me to think of ways we could make our moist convection scheme more generic so that they can handle simulating climates in very, very different situations. And so what do I mean by a generic moist convection scheme? So for me, a generic moist convection scheme is a scheme that is valid for any mixing ratio of the condensable species, because most moist convection schemes that have been created for Earth, where water vapor is only a trace gas, but you have to think of Mars, where CO2 can condense and can create convection, but CO2 is almost a pure gas in this regime. And so it's completely different. And of course, we want to be able to do everything in between these two situations. Then we want also to be, so this, yeah, of course, is to be able to deal with runaway greenhouse planets, present Mars, but also the icy giants at depth where there could be a lot of water, or Pluto also that has N2, that is condensing gas, and CH4 as well. So it should be a scheme that is valid for any combination of condensable species, because of course there could be several condensable species in a given atmosphere. And a scheme that should be valid also for any background non-condensable gas. And I will come to that later. But it's also very important because, for example, if you want to deal with a giant planet where you have H2 instead of N2, it can be really different. But even for, let's say, mini Neptunes, or even just like early H2-dominated atmospheres on Earth-like planets. And then, of course, you would like to have a robust mass flux or cloud parameterization for extreme dynamical conditions. But as you can see, it's already a pretty big topic, so I know I won't have time to talk about that last point. So let's dig in. So when we talk about going towards the non-dilute regime, so the regime where the vapor can be pretty much anywhere between almost 0 and almost 1, then the first thing that comes to mind is generalizing the lapse rate. And of course, you find that in many forms, in many papers that you can see here, and with many levels of approximation, and even sometimes many mistakes. And actually, I think it's just the tip of the iceberg. You just have to be careful with that, but there is nothing really tricky about that. What is really tricky is actually putting your GCM in a position where you can actually really go into that non-dilute regime. And for that, you need to do some preliminaries. So just let's first try to talk about condensation for a while. Because, of course, in the dilute paradigm, the mass of condensable species are neglected. So many moisture variables are equivalent. So, for example, the mixing ratio here, which is the ratio of the density of the vapor to the dry air, is in the dilute paradigm the same thing as the specific humidity, which is the ratio of the density of vapor over the density of the whole gas. And in this paradigm, still for the same reason, the mass of the atmosphere does not change with condensation, evaporation, or sublimation. And of course, we know it's not true when we have some of these processes happening. So basically, if you want to have a generic condensation, the first thing you need to do is to really think hard about the variable you want to use and stick to it all along the code if you really want to avoid any problems of conservation of matter and mass. So for me, I think I tend to use and to like specific humidity, and because it has a special feature, which is that it is still defined when the background gas vanishes. So this specific humidity is 1 when you have a pure species, which is not true for the mixing ratio that goes to infinity. Then that's not completely easy, but that's the easy part. And then you have the more tricky part, which is to take care of the change in atmospheric mass. And it's more tricky than just changing the surface pressure. And here's why. So if you're in the dilute paradigm, if you have some atmosphere column, and then you have some evaporation that's at the surface, but it would be the same if a cloud evaporates or a cloud condenses aloft. So basically what you do is you do not change the column, you just change the amount of the tracer for water vapor. But in fact, what is happening is that when you evaporate some water vapor, you actually increase mass. So in pressure coordinates here, the surface pressure increases because, well, at least in hydrostatic equilibrium. And so, well, then you could just say, oh, I just need to increase the surface pressure when I do evaporate some water vapor. But the problem is that in most climate models, what you are using are actually some what you would call fixed coordinates or terrain following coordinates, like the sigma coordinates or the hybrid coordinates. And the thing is that these coordinates, they are not Lagrangian coordinates. They do not follow the fluid. Because then, for example, if you take sigma coordinates, the sigma 1, which is equal to 1 at the surface, it doesn't change. So basically, in your atmosphere, your surfaces, your interfaces between the layers, they move. And so basically, if you look at here, for example, at these molecules, the molecules don't move from left to right a lot because you just had, like, for example, evaporation at the bottom. But because your coordinate moves, what it does is that in your GCM, it creates some mass, energy, and tracer, and even momentum fluxes between your layers. And you really have to take that into account if you really want to account for these motions that are created by the mass addition or the mass suppression in your atmosphere. And if you want to know a way to do that, there is a recipe. It was first developed by François Forget for Mars, but it was more for a pure CO2 atmosphere. And then it was generalized for water vapor in the dilute to non-dilute regime in our paper in 2013. But just to give you one example of what it actually matters is one example on Pluto, where you can have, for example, N2 mass flows. Here, for example, is a simulation of Pluto in southern winter. And you have here the zonal wind and here the meridional wind. And you see that if you do not account for this mass flow, what happens is that you have a general, like, Hadley circulation, but from hemisphere to hemisphere. It's pretty weak, and it's creating pretty weak winds because of angular momentum conservation. But if you do account for these mass flows, what actually happens is that because you sublime N2 at the surface here, and you create it and you put it at the polar, at the south pole, what happens is that you create an open branch, an open circulation, that it's an open cell, where you only have one branch without the return branch, because actually matter is created here in the atmosphere and is deposited here. And because of angular momentum conservation, this create these big super rotating winds in the south pole, and then create by wave transport some super rotation at the equator. And so you see that there is really a truly qualitative, not only quantitative, but a truly qualitative change in the dynamics of the planet just because you account for that. So I think it's really important if you want to go to this non-dilute regime. Then, of course, when you have taken care of these points, you do have to update your favorite convective adjustment scheme. But when you're there, it's, I think, much more simple. So, of course, you have to change the lapse rate. I won't dwell on that too much. But the important thing is that you have to take care of conservation issues, because some terms in the energy budget are not negligible anymore. And you can see a paper by Fang Ding and Pierre Humbert in 2016 that talks really well about that. But then, even in that paper, it's still a very simple scheme, and in particular with respect to the precipitations and cloud formation. And I think there is a lot of efforts that should go that way if we want to really get a truly robust scheme. Then, well, if we want a really robust moist convection scheme, it should be a convection scheme that at least handles convection inside the solar system. And here is an example of convection in the solar system, which are storms on Jupiter that have been seen by Juno. But we also have this quite extreme example of the Saturn Great White Storms that happen every once in a while. And the thing is that for these environments, convection can be really different, because the background gas of the atmosphere is different. It's not N2, it's not CO2, it's H2. But the question you could ask is, why would convection in hydrogen be so different? Because hydrogen doesn't have, very different relative properties compared to N2. Well, the thing is that if you take your generic, moist terrestrial planet like Earth, then you have convection that is principally driven by thermal gradients, so it's hot below and less hot above. But also, it is helped by the fact that you have latent heat release. That's why we call moist convection, but also because of the mean molecular weight effect, because water has a mean molecular weight of 18, which is a bit smaller than the 28 of the background gas of N2. So what happens is that the atmosphere is, for the same temperature, the atmosphere is a bit less dense here at the bottom, where there is a bit more water than you would have here in terms of mean molecular weight, aloft, where you have less water vapor. And so this mean molecular weight gradient actually helps convection on Earth. So it's not such a big deal on Earth, because, I mean, convection is already efficient. You're just making it tiny bit more efficient. But what happens when you go on a giant planet or a hydrogen-dominated planet? Well, there is one effect which is important, which is you have a dry troposphere down there. But it's not the main effect. The main effect is that your background gas is now H2. And the problem is that now you have a reversal of this mean molecular weight gradient. So you have heavier water-rich gas down there and lighter water-poor gas up there. And that's actually, you can show that it creates inhibition for the convection that is much harder to start. And that is not even considering moist processes, but actually it's been shown that when you do account for these moist processes, you have a pretty simple criterion for when convection can or cannot happen. And actually, it can be shown that convection is just simply shut down by these moist processes when you're just above a critical abundance, which is given by this formula here. And for water in H2, this critical mixing ratio is 0.07. So it corresponds to some gas saturated at a temperature of only like 310 K. So it's not a lot. So it could be really easy on the warm to slightly hot terrestrial planets with a primordial atmosphere to be in a position where actually you completely shut down convection. So what would happen? So that's what we think would happen. So you would have basically your dry adiabat, for example, near the surface where you don't have moist processes yet. But then when you're in this regime where you do have these moist processes, but you're above the critical mixing ratio of water, then you have a very stable layer where the temperature gradient here is a much higher, much steeper than just the moist adiabat. So you almost have a jump in temperature. And then you have, when you arrive below this point where the water vapor is below the critical water vapor ratio, then you do have your moist troposphere, your usual moist troposphere. And so if you look, for example, for Jupiter, here's what you would predict for a typical moist adiabat with the different values of the internal water mixing ratio. But if you do account for the inhibition convection, you see this step, which basically changes a lot the temperature that you would infer for the internal temperature of the planet. And so it's interesting, it's possibly detectable with Juno, although we don't think the mixing ratio of water vapor in Jupiter is quite big enough. But what is interesting is that it actually has been proposed by Lee and Ingersoll that this could be the reason for these huge storms where you would have this inhibition of convection, which now and then could just be broken because you accumulate too much energy down below, and then you just release it in one big storm. So that's a pretty interesting thing to pursue, and I think it's really important to get that if you want to have a robust convection scheme. Because, so of course, it's going to be important even more for Uranus and Neptune because we're really talking about a lot of enrichment. So if you talk in the context of exoplanets, think about the evolution of warm Neptunes, where you could have a lot of water in a hydrogen-dominated atmosphere. But also, it's been also discussed what would happen in a runner greenhouse in a H2-dominated atmosphere. So there was a nice paper also by Daniel Cole who discussed that and who found some interesting new states for these climates. But the thing is that in this paper, they are still considering a pretty just normal adiabat, and they're not at all considering the fact that the convection can be shut down when you have this kind of high water content. And so I think it would change a lot the equilibrium of the atmosphere. So with that, I will just leave you with my conclusions and my personal tips if you want to have a generic moist convection. And I hope you enjoyed the meeting. I hope we can discuss maybe next year or the year after about the other points that we need to do to get the extra steps that I didn't have time to talk about, which are of course the ways we want to how to have a truly robust parametrization for the microphysics of the clouds that are created by convection. Thank you.